seismicity can inform based on the difference between those, and also looking at how crustal fracture networks control permeability, which is critical to geothermal projects, and how looking at seismicity can help us to improve how we quantify and reduce uncertainty in geothermal exploration, and therefore reduce risk and improve decision making in industry. So a really brief intro to Iceland and why this is a really good place to study all of this sort of stuff. So lots of geoscientists are very interested in Iceland anyway. It's pretty geologically unique. So we have a mantle plume and the mid-Atlantic ridge, which when they come together gives rise to this island, which has elevated volcanic and seismic activity. So yeah, we've got a bunch of volcanic and geothermal systems across the island. We've got the plate boundary, which kind of runs through the middle of it. And that makes it a really good, as I've said, natural laboratory with lots of volcanism, earthquakes, geothermal activity, things like that. I'm going to show two different case studies today, both in the southwest of Iceland. So, yep, first and foremost, I was a volcanoseismologist, so I'm sorry if it's a bit volcano-focused to start, with this being a geothermal talk. But yeah, so we have lots of recent eruptions happening over here on the Reykjanes Peninsula, as well as long-lived geothermal systems. So there is a power station. I think there's more than one power station, actually. There is one power station based in the Svartsengi volcanic system. And this is also really near to the famous Blue Lagoon, which is a hot pool that loads of tourists like to swim in. And yeah, there's been recent recent eruptive activity alongside this geothermal activity. And then the second part of the talk, I'll focus on the Hengill region. So this is kind of at a triple junction between the Reykjanes ridge here, the Western Volcanic Zone and the South Iceland Seismic Zone. There is also a long-lived geothermal area here with Iceland's two largest power stations. And there are loads of central volcanoes, although they are not presently erupting. So, part one. This is me in front of some recent lava in the Svartsengi system. This is my office mate, Tom O'Hara, and my other trusty field assistant, Rob Evans, who happens to be my partner. And yeah, this will focus on seismicity, mainly in volcanic systems, which also in this case happen to have associated geothermal activity. So this is the Reykjanes Peninsula. So like I say, southwest Iceland, we have lots of different fissure swarms with volcanic centres which define these volcanic systems. So there are several of these along the peninsula and they all trend kind of in this direction. Down here, if you can see my cursor, can you see my cursor? Sorry if you can't. Is there a way that I can do that? Actually, pointer options. I don't know. Can you see it? Yes, no?
Yes, we can see it.
Yes, you can. Perfect. Thank you. Right, so pointing down here, this is where the town of Grindavik is, which if you've been following any of the recent volcanism on the peninsula, this is now largely deserted. And that's all very sad, and the lava came very close to destroying lots of parts of it. And Reykjavik is off the map up here to the north. So yeah, the Svartsengi power station that I mentioned is just here in the inverted triangle. There's a big mountain called Mount Thorbjorn, and the Blue Lagoon, which I mentioned before, is around here too. So yes, the Reykjanes Peninsula. It was volcanically inactive. Last erupted in around 1240 CE. Parts of it have not been active for a lot longer than that. The first system to erupt was the Fagradalsfjall system, so this one here. And this exhibited 4 different dike intrusions, 3 different eruptions. For anybody who isn't sure, a dike intrusion is like a vertical sheet of magma that intrudes into the crust, and they often breach the surface and lead to eruptions. So yes, this Fagradalsfjall system was the first one to erupt. And interestingly, all of the melt came from depth. So there was no crustal magma storage, no mid-crustal magma chamber, which is a little bit kind of geologically unusual in certain settings. So this was volcanically active between 2021 and 2023, which was most of my PhD. And then there's the Svartsengi system, so just here, just to the west of Fagradalsfjall. And this is where the eruptive activity then jumped after it had started in Fagradalsfjall. This, as I said, has a long-lived geothermal area and a mid-crustal magma domain, which feeds this. So that's different to Reykjanes, which is helpfully explained in this little figure here. So Svartsengi, yeah, we've got magma stored in the crust, whereas Reykjanes, it comes all from depth. And also, interestingly, we had lots of inflationary events. So where the ground motion is detected to be moving upwards in the Svartsengi system as early as 2020. So that was before any of the volcanism in the Reykjanes system. And in total, we had 9 eruptions and 11 dike intrusions, and they lasted, I've said here, 2023 until present. It's actually a little bit overdue. There hasn't been an eruption in a little while, but it's kind of still inflating. We still think it probably is active. So I won't quite say it's over yet. Yeah, so these are quite different, given that their systems kind of just 10 kilometers from each other. I should say at this point, I usually give this talk as a kind of an overview of my PhD work on a dike intrusion in the Reykjanes system, followed by a chat about the Svartsengi system. So this is a little bit new to me, giving it this way round. So this is the overview of what the volcanic activity looked like on the peninsula. We had, like I just mentioned, lots of inflationary episodes in the Svartsengi system before anything kicked off volcanically. So this is the first eruption here. This was happening in Svartsengi. This was a large part of the focus of my PhD research. I can talk about this if you'd like to know. But yeah, today I thought it was more interesting from a geothermal perspective to talk about one of these inflationary events in the Svartsengi system. So yeah, just to kind of put this all in a little bit of context, we had inflation in one system, eruption in a different system, which carried on for a little while, all the while still exhibiting a little bit of inflation in the other system. And then eventually we actually had eruptions in that system as well. So it's all a little bit complicated and all over the place. Right, so talking about the Svartsengi system, so this system with the long-lived geothermal area, mid-crustal magma domain. So we had, as I just said, prior to any eruptions at all, cycles of uplift and inflation were observed near to this geothermal area on the Reykjanes Peninsula, observed as early as 2020. So the cause of these was a little bit debated at the time. As I said, this was largely because we hadn't seen any magma actually erupted. There was no volcanic activity when these started, so people weren't really sure. People tried to model the deformation source. Some people on the left, this figure is from a paper that tried to model this before we knew that there were going to be eruptions in this system. Some people kind of went back and looked at it afterwards. But in general, attempts to study the geodetic response to this event were a bit complicated because these inflations and these intrusions were a little bit slow. So the signal to noise ratio was not very good, and there was a lot of shallow faulting associated with it. So that produced lots of significant surface offsets. So this means that seismicity was a really good way to study this, and people hadn't really done that before. So I should say we now think that this isn't really debated anymore because the magma actually surfaced. We do think these inflationary events were likely to do with magma in the first place. We think they were probably inflation of this pre-existing magma domain. So kind of like sill intrusions, little horizontal intrusions of magma, but as part of this existing magma domain. And also when the eruptions started to happen, these future dikes, as I'll call them, propagated kind of from the northeast corner of where these studies have modelled this sill intrusion to be. So they popped out here. And so there was a question of whether there was anything we could look at if we go back and look at the seismicity that was happening in these inflationary events, whether there was any clues in that as to where these dikes would happen, kind of from a hazard monitoring perspective, and also just to understand this magmatic source a little bit better. So as I said, I usually give this talk with a discussion of dike seismicity versus sill seismicity. And in general, so these vertical sheets of magma, which we call dikes, they're often really well defined by their seismicity. This is an example on the right here from my PhD research, so a seismic catalogue of that first dike that I mentioned. And you can use the seismicity to kind of track the melt propagation really well. And this is not really done so often for sill intrusions. It's less well studied, perhaps because there tends to be a bit less seismicity associated with them overall, and they propagate a little bit differently, and the problem's a little bit harder. But they are still really important. So like they are a hazard in their own right. And as I said, we did end up getting dike intrusions and eruptions from this sill intrusion that happened. So it's important to study it. And it's also just a good academic question to kind of look at different magmatic intrusions in different crustal settings of different geometries and what their different seismicity looks like. So my PhD group set up a monitoring network on the Reykjanes Peninsula. I think this has been running since 2020. There were stations there before as well, operated by different people. So all of these different institutions are operating stations on the peninsula. And this makes it a really, really dense monitoring network. So possibly some of the best instrumented intrusions of this type ever. Definitely with all of these stations, some of the best within the region. And I've been very lucky to get to do a lot of field work over the years. So this is me servicing the seismic network. This is our colleague Sven, colleague Connor, colleague Tom Winder. So that's just some kind of gratuitous fieldwork photos just because they're nice to see. And yeah, basically, I started off by making a really detailed catalogue of seismicity using this amazing network of seismic stations. So in general, in this talk, I've kind of gone a little bit light on the methods. I wasn't too sure on the background of those of you watching. So if you do have questions about the methods, please ask me. I'm happy to chat about them. But basically, you detect earthquakes with the seismometers. You can then make a catalogue, locate those earthquakes using travel times. And this seismicity is also relatively relocated, which means that if you look at the different earthquakes relative to one another, you can get a more accurate picture and eliminate some of the uncertainties involved in the initial earthquake location process. So this video here is showing a map and a north-south cross-section through the seismicity. So this is a zoomed-in area before. This is the power station in the Blue Lagoon. And the catalogue spans the month before the intrusion and the month during. So the intrusion lasted for about a month, started at the very end of April, ended at the end of May in 2022. So, and there are a few things to see. Basically, the seismicity is quite diffuse over the area, and it's not super intense. So if you think back to the quick video I showed of the dike intrusion, there was loads of seismicity everywhere. It was really propagating. It was really intense. And this generally overall looks quite different. So this is the same seismicity, the same map. This time this cross-section is along this line rather than north-south, coloured by time as per the movie. And we can start to see some individual faults that are maybe picked out by these individual earthquakes. In the cross-section here, we can also see kind of a vertical expression of some of those. And there's an interesting sort of domed shape to the intrusion, or to the seismicity, sorry, that's visible in the cross-section. This here, this line is the modelled sill source from the paper I mentioned earlier, so Michelle Parks in Iceland. So that's kind of where they think the magma itself is likely to be. And this is where we see the seismicity happening above that. It's a good time to talk a little bit about the seismicity, the tectonics, sorry, of the Reykjanes Peninsula. If I can just make that go again. So this little graphic here, the Reykjanes Peninsula is an oblique rift. So we've got divergent plate boundary, but that plate boundary is orientated not perpendicular to the actual direction of extension. And what that is expressed like is we have mostly a network of north-south faults which move in a strike-slip manner, so kind of as this little cartoon is showing here. So we pull them apart and they rotate a little bit like books on a bookshelf. So we call this bookshelf style faulting. There's also some normal faulting, and a lot of the extension is also taken up in magmatic episodes, so as we have seen in recent times. So looking at the spatiotemporal variability, these are some timelines that I put together. So we've got longitudinal variation, latitudinal variation in depth over here. None of these kind of show very much at all. So again, I keep mentioning that dike intrusion. You really see it propagating back and forth. And with this, you don't really see that at all. So there's no real clear trends throughout the intrusion period, which is this orange shaded box here. It's kind of fairly consistent throughout. There's also very little change in the magnitude or the mean magnitude, which is the solid line here. We maybe get a couple more of these larger magnitude events. There were a couple of events that were around magnitude 4 or more. All of this is probably by most people's standards classed as microseismicity still, but you definitely would feel a magnitude 4, and you would certainly you'd still feel magnitude 2s or 3s if you were in the town of Grindavik that I mentioned earlier. This is the earthquake count down here, and you can see there is a bit of an uptick in number of events during the intrusion period. But yeah, generally it seems quite seismically sneaky, this intrusion. There's not a huge amount to see, really. So another thing that I did, this jazzy figure here, was to do some what's called manual analysis of the earthquakes and make something called fault plane solutions. So I spatially selected a bunch of kind of lineations of earthquakes here that you can see. So ones that look like they might be lining up along a fault. In the background of this plot are all the mapped surface fractures in the region, and these are coloured by strike like this, which will be important on the next slide. And the point of this study would just be to see whether the seismicity tends to be happening on pre-existing faults or whether we're actually seeing new faults activated here that we haven't seen before mapped at the surface. And so a way to do this would be to compare the strike, both of the faults delineated by these groups of hypercenters, these swarms, to the map fractures, and also to look at the individual fault planes. So I manually analysed around 85 earthquakes and made these things that I mentioned called fault plane solutions. Some of you may be aware of what these are. It's basically a way that seismologists characterize the actual motion in an earthquake in terms of slip on the fault. So down here in the bottom right, there are broadly 3 categories of slip. Sometimes you get a combination of them, but you can have strike slip motion, which is where the plates move side by side, or you can usually on kind of vertically dipping faults, or you can have dip slip motion along dipping structures. And what we see mostly in my fault plane solutions here is strike slip motion, and we represent those on a hemisphere plot as I've put in these cartoons down here. So yeah, the point was to look at the strike of these individual fault planes and not just the alignment of the earthquake swarms. We find almost all of them are strike slip faults, and their fault planes do tend to align well with the mapped fractures. So I've sort of tried to show that here with the colour of the beach balls matching the colour of the jazzy fault maps that I've put on the back of on the back of these plots. And yeah, some of them you can't always tell which of these 2 planes that you see represented on the beach ball are the fault plane. Sometimes you need geological evidence, things like that. In general, we found good agreement between one of the planes and the lineations of the hypercenters and the mapped fractures. So generally, what all of this is getting at is that a lot of this seismicity was happening on pre-existing structures. This is a cross-section again, and you can sort of see this is rear hemisphere projection now, and you can see a vertical fault plane for most of these events. So most of these earthquakes that I've manually analysed look like they are happening on map structures that we knew about, and they seem to match the overall tectonic regime. So what we're trying to say here is that these are generally triggering faults that were already active. So this is just another little plot to try and investigate that a little bit further. This is those red selected faults on the previous slide, just as little timelines on their own. And again, this is the intrusion period shaded in orange, just whether to see whether these faults that we see being activated during the intrusion in the orange bit were also active maybe prior to the intrusion, which might suggest that they were already there, already being tectonically activated. And yeah, to be fair, we do see that in a lot of places. So this just adds weight basically to the argument that this sill is pretty much only triggering seismicity on pre-existing structures. We're not getting new fractures created as a result of this intrusion. One more thing that came out of this work was trying to define the base of seismicity. So I mentioned a few slides back that we saw this kind of domed base of the seismicity in cross-section that was quite sharply defined. And we kind of care about this because seismicity can only occur where the crust is brittle in general. Brittle tends to mean colder. And so where there is no seismicity, the crust is likely to be hotter. And so from a kind of geothermal perspective, and whether we care about where this heat source is in terms of this sill, we can sort of see that expressed in the seismicity, perhaps. So yeah, I basically just fitted a line across these various profiles to where the 95th percentile base of seismicity was. And yeah, we see generally on this, the A to A prime and the C to C prime, we sort of see this domed shape. And near to the very center of the inflation here, which is represented by this star, we see this really big kind of shallowing here. So this is where we think it is really hot. So basically this is basically saying that I think where those previous studies had modeled the center of that sill inflation to be, we kind of see agreement with that in the seismicity. We do see it a bit shallower than they see, but that might just be, as I've said, that seismicity can only occur where it is more brittle and colder above. So we're not really likely to see seismicity jutting right up against where that sill intrusion is happening. And this also gives way to the slight debate that I mentioned before of whether or not there was a pre-existing magma domain. We're pretty sure that there is now. And yeah, we were able to say that all of these observations are kind of in agreement with each other. So to kind of wrap up that first section of the talk, we previously had this debate about the origin of these inflationary events. And this study helps us to agree that probably actually it is intrusion or inflation within this pre-existing magma domain. And this kind of cartoon over here sort of shows what's probably happening. So we're likely getting magma intruded, probably near the top of this pre-existing hot domain. That's applying a sort of flexural bending stress to the crust above. What that is then doing is activating these pre-existing structures. We're probably not creating new fractures as a result of this. It's probably not magma intruding into like brittle, cold country rock. It's likely this intrusion within kind of ductile part of the crust that's causing stresses on the crust above. And in general, the extent to which seismicity can inform the kind of location, timing, and extent of the sill intrusion is quite limited, especially relative to dikes. It largely occurs on these pre-existing structures. As I did say, the seismicity in itself of the sill is a bit of a hazard. So we do get these kind of large events, which if you're right nearby are quite significant. But it was also quite difficult to identify any sort of precursors that might have suggested that where the subsequent dikes that we now know were later going to occur, we can't really tell from the sill seismicity alone where they were likely to happen. And yeah, again, as I feel like I've said a few times now, dike intrusions are often really well delineated in their location and their propagation by the propagation of the seismicity itself, particularly on the Reykjanes Peninsula. And seismicity is really useful for those in inferring where the magma itself exactly is. With the sill, it is more diffuse. It's less intense. It lacks these spatiotemporal trends. However, there's still definitely merit in studying this further. It does require this really dense seismic network, so that's probably why it hasn't really been done before, because it is less intense, it's harder to pick up. And yeah, there's certainly a lot of merit in kind of looking at the profile of this, looking at it in cross-section, things like that, and to give us a bit more certainty on the origin of these events. So kind of wraps up the PhD section of the talk. And now I'll move on to the work that I've been doing during my postdoc. So this is on the Hengill geothermal area. And I'm going to talk about seismicity in specifically geothermal systems, which in this case are also ancient volcanoes. So a quick bit of background to the project. Fractures in the crust can act as permeability pathways. So this is something that geothermal companies are very interested in for the circulation of geothermal fluids. And one way that we're trying to look at this is to look at something called seismic anisotropy, which refers to the directional dependence of wave speed as seismic waves travel through a medium. So I will talk about that a little bit more in a second. And the motivation of this study is to improve the understanding of the subsurface in these regions of interest using anisotropy. And so we can hope to help quantify and reduce uncertainty in geothermal exploration and therefore help to de-risk decision making in the industry. So the study area Hengill, we're still in the southwest of Iceland. It's about 50 kilometres east of Svartsengi that we were just talking about. And as I mentioned before, it's situated at triple junction between the Reykjanes Ridge, which was where we were on the Reykjanes Peninsula. There's the Western Volcanic Zone and the South Iceland Seismic Zone. There are 3 central volcanoes in the area, and each of these has associated geothermal activity too. And we also have 2 of Iceland's largest geothermal power stations again. So this is the Hellisheiði plant here and the Nesjavellir plant up here. And these have been in operation since, I think, respectively, the 90s and the early noughties. The local tectonic regime is pretty similar to further west on the Reykjanes. It mostly involves seismicity upon a network of mostly north-south to northeast-southwest trending faults, which accommodate extension through a mixture of strike-slip motion and rotation, some of that bookshelf stuff that I was talking about just before, a bit of normal faulting as well. And so hence we have elevated tectonic seismicity in the area, and we also have seismicity associated with the natural geothermal activity, as well as induced seismicity relating to the power station's operations. And all of this makes it a really great place to experiment with ways that seismicity can be useful for geothermal exploration. So, which brings me back to this topic of seismic anisotropy. So this was pretty new to me a couple of months ago, so I'll try and go a little bit slower here. So when seismic waves propagate through a medium, anisotropy refers to whether there is a difference in the speed of that propagation based on the direction. So if you have particular things in the crust that make that seismic wave travel faster or slower, depending on where it's traveling. So I'll try and give you just what you need to know here. Anisotropy comes under 2 broad categories. So you can have intrinsic anisotropy at the crystal lattice level, or as is common in the shallow crust, you can have effective anisotropy, which can arise from several means, but typically includes the preferential opening, closing, and alignment of microcracks in a material in response to a stress regime. And those other things that can cause it are also like large-scale structures like faults or dikes. And a good way to measure anisotropy can come from looking at shear wave splitting. So seismic waves have 2 types. So you have compressional P waves and you have transverse S waves or shear waves. When those shear waves enter an anisotropic medium, they will split into a fast and a slow component. And one of those components, the fast orientation, aligns itself with the orientation of any anisotropy present, and the slow orientation is perpendicular to that respectively. And from this measurement, you also get a delay time, which can indicate the strength of the anisotropy or the strength of the splitting, so whether it's weakly or strongly anisotropic. And in order to measure this, we need some recorded seismicity. So the Hengill area is a really great place to do this. It's been really well monitored over the last several years by a combination of institutions. So this is publicly available data this time, I should mention. So before my PhD work, that was all data acquired within my research group. This is all publicly available, nothing to do with me. I'm just using it. So yeah, these stations have been operated by the following institutions here. So they've been operated by the Icelandic Meteorological Office, by Orkuveitan, which is Reykjavik Energy, which is the energy company that operates these 2 geothermal power stations, and then recently this co-seismic project here, so by Francesco Grigoli et al. So yeah, publicly available seismic data sets. I think there were 44 stations, and this the data set that is publicly available spans 2018 to 2021, so well within the production cycle of these geothermal power stations. So as I mentioned already, the area is pretty seismically active, and ESAW, which is the Iceland Geosurvey, have compiled an earthquake catalogue of around 15,000 total events, which I'm showing on the map, which again were all between 2018 and 2021. They located these using manually picked P and S wave arrival times. So this is our source of shear waves from which we can make shear wave splitting measurements using these really reliable manually picked S-wave picks. So an actual person has gone and looked at these. They're really precisely done. So this makes up a larger and higher quality data set than any previous studies in the region. And so there's pretty nice kind of aerial coverage of this catalogue in space and also in time. So these are coloured by time, these earthquakes. And you can also see this in cross-section. So in pink and in purple here are the geothermal injection and production wells, respectively, in the cross sections. There are several clusters of seismicity that are sort of around these wells. So perhaps these represent some of the induced earthquakes. And generally, there's lots of good seismicity coverage in depth too. Lots of the induced stuff seems to be between about 2 and 4 kilometers depth. And we've got some slightly deeper stuff, kind of especially off to the north and the east. So another thing, don't want to get too into this if this is a little bit seismology heavy, again, depending on the audience, but basically we have a 3D model of the seismic velocity structure of the crust in this area. So this is also publicly available. This is from Wu et al. 2024, and you can do what's called ray tracing between each earthquake source and each seismic station to see exactly how a seismic ray between that source and that receiver would travel through this particular seismic velocity structure. So we're really lucky that that 3D model exists, and this little graphic here shows us that we've got pretty good ray path coverage of the area, and so that equates to the sensitivity of where we can be sensitive to anisotropy through these measurements of shear wave splitting along these particular ray paths between these earthquakes and these stations. So again, little bit of methods this time, but I will keep it quite light. Use some in-house software to do the shear wave splitting analysis. This is called SeisSplit. So this makes automatic measurements of shear wave splitting for a given earthquake catalogue that you give it and a station set that you give it. And I've done this so far for all of the events in the catalogue over magnitude 0.7, which was really just quite an arbitrary choice based on the storage capacity of my laptop at the time. So we may expand this in the future. So we have a few other filtering factors for the data that went in. We set a maximum delay time of 0.1 seconds, which is a prevention against something called cycle skipping, which is a common cause of problems in shear wave splitting measurements. We also have a bandpass filter of 0.5 to 10 hertz. And I tuned these parameters after doing some manual measurements and carefully inspecting the outputs before settling on these, thinking these work quite well, and then applying it to the automatic method. So the automatic method ended up spitting out tens of thousands of splitting measurements from around 1,800 or so earthquakes going in. On the right here is an example output plot that you get from SeisSplit. So you see the input traces here, and you see the fast and the slow component here in blue and red. So you can see that split. That's the delay time between the two. And then you get, I don't want to go too much into this. Please ask me if you would like to know more, but essentially the shear wave splitting process changes what is initially elliptical particle motion into linear particle motion. So this linear particle motion is that fast orientation. So the orientation parallel to the anisotropy of the fast component of the shear wave. And then afterwards, we also do some quality control, filtering the results on things like signal to noise ratio. SeisSplit gives us a quality value out. And then we also get an uncertainty on the orientation of the fast polarization. And then after we do this, we end up keeping some thousands of splitting results, or around 5 to 10% or something of the total number, depending on those filtering values. So I'll finally show you some results. So this map is showing circular histogram results of this fast orientation that I mentioned from just under 2,000 splits. So using these parameters here. So these are quite harshly filtered. These are kind of the best of the best events. High signal to noise ratio, high quality value, and really low, less than 10 degrees uncertainty on that fast orientation. So the results are binned by the station location. This does result in a little bit of spatial mushing, but it does tend to provide a fairly decent reflection of the lateral variation in fast orientation. And basically, so some first order observations that come out show that lots of the fast orientations in general tend to align roughly parallel with the regional rift fabric. So in this plot, the Black lines are mapped surface fractures. The red lines are historical eruptive fissures. And lots of these circular histograms here are in alignment with that. The really interesting bits are the notable outliers. So one is, are they going to pop up? Yeah. One particular one here is almost 90 degrees basically to the mapped surface fractures, which is really, really interesting. So this also happens to be around where a lot of the geothermal wells are located. So those are the grey squares that you can see here. Maybe we've got a little bit of offset up here and up here, but particularly these ones here near to where they're doing a lot of the production. So while these results are pretty preliminary, this is really quite stark. This is something we're looking into with a lot of interest, because seeing these kinds of rotations in these areas where we know that there is activity relating to the geothermal power station operations is really quite striking. So this is kind of like a real thing to look into in lots of detail. To enable useful comparison of the delay time measurements, so this other quantity that you get out from the shear wave splitting, you have to relate it to the path length over which it's accrued, and the average shear wave velocity over that ray path, which, as I said before, we've traced nicely through our 3D velocity model. And this lets you define anisotropy as a percentage using this equation. Now, I am not a mathsy person at all, so please don't be terrified by the equation if you are unmathsy like me. But basically what this boils down to is that if we had homogeneous anisotropy throughout the region, we would expect some sort of relationship like this. So this is example data, but basically you would see measurements of the anisotropy cluster around a single value at all depths, basically. So if you just had a fabric causing anisotropy that was all the same, this is what you would see. What we actually see is a little bit different. So this is real data now. We get this sort of relationship emerging, whereby we have variable anisotropy in the shallow crust, and most of it is seemingly accumulating in the top couple of kilometers, and it's sort of decreasing with depth like this. And this kind of follows if we think that anisotropy, as I said right at the start of this section, is likely to be caused by fractures at some scale within the shallow crust, which are likely to close up with pressure as you get deeper in the crust. So kind of seeing something that we would expect. And we can go a little bit further to actually try and constrain the depth at which most of this anisotropy is accumulating by considering only part of the ray path. So this little cartoon in the bottom left that I showed before. So if we just consider the very top part of that in the sketch plot and use just that in our calculation, we can see that this kind of removes that effect of the anisotropy dropping off with depth. And we've done this here for 2 kilometers and above the very top part of the ray path. It kind of flattens out that trend. And so this allows us to say that most of the anisotropy is being accrued just in that shallowest part of the crust, which, as I say, is in line with expectations. I'm going to speed up a little bit here because I do really want to talk about just the last few slides and the implications of this work. But basically, we can display all of this information on a hemisphere plot again. And we can also talk about the direction and the strength of the anisotropy on a plot like this. So if we think about azimuth and inclination angle from the vertical of a ray path between the source and the receiver, like in this diagram, we can make a plot like this. So here, ticks are orientated within the fast orientation, and they're both length and color scaled by the strength of anisotropy. This is another synthetic plot, for example, data showing what we'd expect by fractures orientated in kind of the regional tectonic regime that we have in Hengill. So orientated northeast southwest, we get strongest anisotropy for rays traveling parallel to the fabric with near vertical incidence angle. And that actually kind of is quite similar to what we observe. I'm going to absolutely whiz through this just because I've noticed the time. But yeah, so we do tend to get stronger anisotropy in the center and for more vertical rays that are orientated in the direction of the regional fabric. We do have that local variation, just like when I showed the map beforehand. So this is just the observations for a singular station here, which is actually quite near to the flipped results that I showed, this one, and also, yes, kind of in between, it's the station here. And you can see that the ticks are kind of showing that other orientation. So just again to say that we have local variation in the anisotropy, which is really interesting, and we can interrogate that in various different ways. So that's where I'm up to so far in terms of the preliminary results, but there's loads and loads of scope in the data set for future work to carry that forward and to try and answer these sorts of questions. So we're really interested in what's actually controlling this anisotropy. So is it these microfractures relating to the stress regime? Is it larger fault structures? And are these orientated in the same way as one another, perhaps? Maybe are the map fractures at the surface the same structures that are controlling the permeability several kilometers down? And crucially, what do those really stark rotations in anisotropy near to the geothermal areas, what do they mean? To do this, one thing we're going to try and do is look at the crustal crack properties. So maybe doing something like effective medium modelling and comparing those to our observed splitting results and to the mapped fractures. Maybe we can go further to model how different layers of anisotropy at different depths can affect the splitting and compare this to observations too. My colleague Brandon has been doing some P-wave anisotropy, so that's just looking at the variation in P-wave travel time. And so we're going to try and integrate those results with the shear splitting, see whether they differ and whether they're the same. And really excitingly, maybe, just maybe, we're going to try and push this even further to investigate, perhaps, can we see changes in the shear splitting and the anisotropy through time? And can we link this to perturbations in the stress state of the crust? Perhaps due to the geothermal power company's operations. So the real holy grail will be to do some geomechanical modelling of this and to see if we could truly link anisotropy really closely to activities like this. That would be really fantastic. Obviously, ideally, geothermal companies make quite a lot of effort not to perturb the stress state. So perhaps if we find that it hasn't changed through time, that would actually be a good thing too. But yeah, we're going to try and look at that and try and find some older data. So in terms of implications, we're really lucky to have been able to make such a detailed study of anisotropy in the region with a really great data set. And while the results are preliminary, we're already able to constrain a lot of the anisotropy to within the top 2 kilometers of the crust. And while a lot of the orientations are aligned with the rift fabric, there are these notable rotations near the geothermal production areas. So they're really exciting, and they indicate to us that anisotropy could really be a key method for geothermal exploration. And going forward, we'll be really trying to understand the physical mechanisms governing these changes in anisotropy and looking for more information from other means like the geology. We've got borehole data, all sorts of stuff like that, if I can get access to it, and ultimately hoping to show that anisotropy could be a really useful tool to investigate and characterise geothermal reservoirs and provide some real-world context to industry problems in characterising geothermal targets. So this is the bit I really wanted to get to. It's just a quick slide, but I get quite a lot of eye rolls from people, particularly within the geothermal industry in the UK, who are like, well, obviously this works in Iceland. They've been doing it forever. They've got loads of seismicity. They've got loads of the means to study all of this stuff. So we know that there is merit in studying seismicity where we have plenty of earthquakes. But this is just to highlight one really cool case study. So I'm plugging other people's work here at the end of my talk. And there are also plenty of other projects within the UK who are doing similar stuff to this. But basically, you can do this in the UK too. This has been proven. So this study by Tom Hudson et al. In 2022 was a really successful study of some induced seismicity over quite a short time period, I think just 3 weeks or something, at the Eden geothermal site. So they deployed a really dense network of nodal seismometers, and they did find lots of seismicity, and they were able to make fault plane solutions. They were able to look at seismic anisotropy and things like that. So yes, perhaps your resolution is going to be decreased where you have less earthquakes going on, but it's really not hopeless. And as I said right at the top of the talk, lots of people kind of only sit up and listen about seismicity in general in terms of not wanting to induce loads of earthquakes, but actually they have a real use, these earthquakes, for actual exploration, telling us about the subsurface. So I'll leave you with this. Seismicity as a tool is overlooked, so it can really help to increase our understanding of permeability in the crust, which is vital for geothermal projects. And monitoring this can provide you with information prior to drilling holes. You know, this is all possible to monitor from the surface. You can do it in areas of poor surface fracture exposure at relatively low cost. And I really think that seismicity is kind of the future in reducing uncertainty and therefore reducing risk to the geothermal industry. So thank you for listening, and happy to take any questions.
Thank you, Esme. That was great. Yeah, that was really interesting. And as on top of the science, I really enjoyed the phrase seismically sneaky, and I will be adding that to my day-to-day. Right. Well, we do have a few minutes for questions. So if anybody has any questions, if you'd like to raise your hand, we'll get round to asking. We can ask you to unmute and come up with some questions. I have just noticed a couple come through on the chat. First to Carol, we've actually been recording this, Carol, so it's going to be shared on our YouTube channel. So you'll be able to see all the slides on there, which I hope is helpful for you. But we also have a question from Hester, who I've seen has just put her camera on. Hester, do you want to ask your question? No, she doesn't. I'll read it out. She's in the office. Okay. Question about your PhD work. Is it most applicable to the supercritical geothermal projects, perhaps to replicate or prevent a similar event to Krafla?
Oh, right. So does this mean drilling into magma? Is this what this question is about?
Yes, I think that's what it's about.
Well, I should say, actually, there are lots of projects that are really trying hard to drill into magma deliberately. Not quite sure why. Sorry, the question was, is this most applicable to kind of avoid disasters like that? I suppose it is very nice to know when you are likely to drill into magma, especially if that is not your intention. So that would definitely be a perk of that sort of study. I'm not really sure. I think so. Let me start again. The seismicity study for my PhD was really done as kind of a comparative study to the dike, which I did say, yeah, as I said a few times, sort of struggled to discuss it kind of on its own as a standalone study. With the time, it's classic PhD problem, with the time that I had in the PhD, I would have liked to have gone a lot further. And I do think there is a lot of merit in a detailed microseismic study like the one I did to help understand a lot more than just, are you going to drill into magma or not? Since I've started my postdoc, I really think the seismic anisotropy particularly is perhaps the most interesting from an exploratory perspective. A lot of promise there for that. But yeah, I guess seismicity is, I don't know if it's going to stop you drilling into magma or not. It's an interesting one.
Okay, Sonic, someone may be doing another PhD to follow up on.
Thank you for the question.
Does anyone else have a question they'd like to ask out loud? If not, I have one to read out. Oh, yep, someone's popped their hand up.
I've typed mine in the chat, but I'm happy to ask out loud.
Go ahead.
Thanks. Interesting presentation. It's a whole world I'm learning about since I started my job 6 months ago, work for a silicon microgravity, a gravity sensing company. So the question from me is, do you use gravity data to process with your seismic data?
I haven't personally. So I'm not entirely sure, partly because a lot of the papers on the geodetic modeling are kind of nature paper style things where the methods are kind of buried in the supplementary and quite difficult to access. I think some of the groups in Iceland who are doing the geodetic modeling have looked at that sort of thing. I personally haven't had access to that type of data. I'm trying really hard to get access to as much of the data that does exist for Hengill as possible during my postdoc. So I only started the postdoc 2 or 3 months ago and haven't yet managed to have a meeting with the energy companies, but they are partners on the project. So yeah, if they've got any data like that, then I'm trying to incorporate as much different data as possible to kind of support the seismicity observations. So yeah, it would certainly be very interesting.
Great, thanks.
I can see we've got a question from Alex Hudson, if you'd like to unmute and ask your question.
Hey Esme, thanks for the presentation.
Hello.
That was awesome. I've got a question and it's probably stupid, so feel free to say if it is. The fast splitting directions you binned by receiver, is it possible to observe them in 3D space, i.e. how they change with depth and XY? So can you make a 3D map of the fast splitting directions, or is that a stupid thing to suggest?
No, it's definitely not stupid. So anisotropy is a weird one because what you record at the receiver is kind of an accumulation of everything that ray path has seen. And so yeah, when I was trying to show these little cartoons at kind of clipping the end of the ray path, that was kind of an attempt to iron that out in terms of how much anisotropy we're seeing. But in terms of the fast, that's kind of only really the delay time. In terms of the fast orientation, you're kind of only going to see the last little bit that it goes through, I think. If anybody has been working on seismic anisotropy for longer than I have, feel free to jump in here. So the Hudson et al. Study, like I say, I need to reread this since starting the postdoc actually, because I mostly read this when I was working with you guys at Cornish Lithium. So they have managed to correlate it with the borehole logs at least, I think, which does obviously give you some 3D constraint. If you had a really complicated scenario where you had a totally different orientation of fractures at depth to the surface, that would probably be quite difficult to see in the anisotropy alone. So yeah, I mean, similar to the question before, like it's kind of the thing where you would do best by kind of bringing in lots of different data sets if you do have borehole logs and things like that.
Okay, thanks.
Okay, great. Well, I think we are coming to the end of our time. So I'd like to first say thank you very much to you, Esme. That was a great talk. It was really interesting. And thank you also to everyone that has attended. I would like to give you a quick plug. I hope you can see my screen. I unfortunately, oh, there we go. This is our next talk on the 27th of May. We're going to be veering away from the extremely hot world of Iceland and magma, and we will be going down a mine instead. So this is going to be Dan Whittington, who's going to do a talk for us on the exploration for mine water resources with some case study sites in Scotland. So I guess I'd like to say thank you very much one final time to Esme. Thank you very much. It was a fantastic talk, and everyone please come along to our next one. Thank you very much, Esme. And I believe the link is in the chat. And with that, I will close us out.
Thank you very much.
Thanks.
Great. I think that went fantastically. I think you timed it perfectly well.
Thank you. Yeah, I did. I skipped over a bit of the boring hemisphere plot stuff.
I thought that was really interesting. Thank you.
Thank you. Thanks.
It was great. And a lot of very nice figures.
Oh, yeah. Thank you. I really like making cartoons and stuff. So bit like
it really helps.
SciComm sort of. Yeah. Find a nice way to. Really helps me as well, because like my postdoc, which I started a couple of months ago, is like very different techniques.